Welcome to Life Cycle Talks, a series of talks presenting the research front to keep you up to date with the science and application of the life cycle perspective. Today's Life Cycle Talk is LCA for optimization in early design phases of buildings. And we will increase our knowledge and understanding of the role of LCA for optimization in early design phases of buildings. And our speaker of today will show us different examples of application such as structural optimization of ceilings or energy renovation of residential buildings. My name is Anna Wikström, and I'm happy to welcome our guest for today, Alexander Hollberg, Associate Professor in Computational Sustainable Design in the Division of Building Technology at Chalmers University of Technology. Warm welcome, Alexander.
Thank you. It's a pleasure to be here.
Great, thank you. And before we start, I just want to inform you about some practical information. All Life Cycle Talks will be published and available on the Swedish Life Cycle Center YouTube channel, and the raise hand function will not be used in Life Cycle Talks, but you can ask questions in the Q&A, and I will pick up questions from there for the question part later on after Alexander's presentation. And back to you, Alexander. I'm curious, what prompted you start studying this research field?
Well, when I started as a PhD student in Germany, I was actually asked to develop a facade that saves at least 70% of greenhouse gas emissions. And then I looked around and I wondered, how do you actually measure this? And I had never heard about LCA in my master study, so I wondered why that's not the case, if there is such a great method out there. And maybe one reason is that it's quite complex for non-LCA experts in the field. So my PhD topic was finally found by trying to simplify LCA for architects and designers like me.
Great, thank you for sharing that. And now, please, it's time for your life cycle talk.
Yes, thank you very much. I'd like to start in by zooming a bit on the title and ask, why is it actually worth to look at buildings? Well, if we look at the Swedish case, we see that buildings and the construction sector are responsible for about 21% of the greenhouse gas emissions, but also a lot of other environmental impacts. For example, 40% of the waste comes from construction sector. And looking globally, these numbers are even higher. So this means we as actors in working with buildings in the construction sector have a big responsibility, but also a big potential to improve things. Why do we need LCA then for this? Well, we've been talking about energy efficiency in buildings since some years, and since the oil crisis in the 70s, there have been in most European countries energy regulations trying to reduce the energy consumption in the use phase of buildings. And this has been quite successful, so we see that the overall greenhouse gas emissions from existing standards to new advanced buildings, for example, passive house, has been lowered. But we also see that the share of embodied greenhouse gas emissions, meaning the emissions related to the production of the materials used in the buildings, has risen. And now we are at the case where it's, let's say, 50-50 over a life cycle of 50 years of a building. So it's clear that we have to look at those so-called embodied greenhouse gas emissions or embodied carbon to make sure we can improve buildings holistically. And why early design phases? Well, if we look at the design process of a typical building, we can split it into different design stages. For example, stage the brief, the concept, typically that's the level of an architectural competition. Then a detailed design where usually technical drawings are done, and finally construction and the use phase. And if we want to do a very accurate LCA, it's clear that the accuracy rises, and when we're in the use phase, we can actually measure energy consumption and do a very accurate LCA. However, it's very difficult, if not too late, to change something then. So the potential to improve and optimize the building is highest in these early design phases, where we have the challenge that we have very little data. Now in Sweden, they have a special case that in January 2020, so-called climate declarations have been introduced for buildings. So if you want to build a new building, you have to calculate the climate impact of the main structure of your building and hand it in together with the building permit, and also when finally getting all the building documents submitted. In order to do this and to limit the effort, there has been a so-called climate database developed as a basis. And this is the idea to not have LCA only or have special experts to do it, but simplify the process, meaning you can use this free database where you find generic values for global warming potential, and you just have to calculate the mass of material and multiply it with those values. Generic values means here they're not product or manufacturer specific, like, for example, environmental product declarations, but they try to represent the average typical building products in Sweden. There are two challenges with this. Well, one is they only look at the production-related impacts. So if you're familiar with the European standard, you might recognize these life cycle modules, A1 to A5. This means these are the stages of the life cycle that are related to the production of the material and also the construction process. But then during the use phase, we have the replacement typically of some materials that don't last as long as the 50 years we usually use for calculations. So maybe we have to replace some windows, which can have a big impact. And also, of course, we want to include the end of life, or maybe even reuse, recovery, recycling potentially if we want to go towards a more circular approach in construction. Another challenge is that declaring the impact is good because you create new knowledge that's still quite limited. And the idea is in some years to use then these declarations to define a limit value and by this try to improve the buildings. But this doesn't help on the individual building level. So my opinion is that besides declaring, we also need to optimize. And there are different ways to do this, but during my PhD processes, I developed this parametric model following more generative design approach, which was quite popular in, or still is very popular in architecture and also engineering office. So the idea is instead of drawing a building and having it fixed, you define it by some parameters, for example, the length and width, and then you can flexibly change things. You can also define your building materials and the technical services you use. And of course, as another input, you need to know where the building stands, where what outdoor temperature you have, for example, which users do you expect in the buildings, what internal set points do they want. And once you define those inputs, this can all be linked, and then the computer can take off the task of calculating the heating demand, energy demands, calculate the mass of the buildings, necessary replacements, and finally, the whole impact over the whole life cycle. And if we want humans to use the results and improve the building, we need to somehow visualize them so people can understand and identify the optimization potential. And then designers can use the information to iteratively change some inputs, see do I get better or worse, and in this iteratively circle, improve the building. Or we can hand over this optimization task to the computer, which I will also show a bit later. Now, it's great to come up with such a model to write some papers and get a PhD, but if we really want to have impact in practice, we also need to implement such models in tools. And I've been involved in a number of tool developments during a postdoc in Switzerland for the Swiss context. We started with some developments now in Sweden, but here I want to show examples of the tool that was, which actually developed as a commercial tool in Germany because we founded a startup based on it. And the idea is to bring this whole calculation and visualization into the environment of the designers, meaning designers typically use simple 3D models in early design phases, for example, in a tool called SketchUp. And they draw these massing models, and that's exactly the time when you can still easily make changes and you have some information about the model to allow you to calculate. So once you have your 3D model, you can define some materials, and then the tool can calculate different indicators as an output, for example, the global warming potential over the whole life cycle, and show this in kilogram CO2 equivalent per square meter and year. And then the interesting part is now designers can start to compare different alternatives. So for example, if you rotate the building, you change the orientation, this will have an impact on the solar gains that the windows have, which will have an impact on the heating demand, and this impacts the whole life cycle. Or if you increase the volume, of course, you need more material, you have more heated volume, but also more space, and this has an impact. If you change the materials, this also has an impact on the thermal properties, for example, the U value of the wall, the amount of heating energy that is lost, and also the embodied carbon. So all of this is connected. And finally, also the technical equipment has a big impact. So if you use a heat pump or district heating gas, all of this changes the life cycle greenhouse gas emissions. And you can, in this iteratively kind of playful way, now improve your building. And I want to show some examples of projects where this was done. So if we look at the very early stage, this design brief, where usually it's actually before some designers are involved, we had a project with project developers that said they want to launch an architectural competition and they want to be sustainable, of course. So they want to define a target for also greenhouse gas emissions, but they have no idea what's actually possible. So they used a tool to come up with a preliminary design of the area they want to build, and then test different materials, different types of basements, heating system, different window sizes, so window to wall ratios, and photovoltaic options. So in total, this would lead to 324 combinations, and it's clear that manually there's too much effort to do this. So they use the tool to run through it and then plot the results, and you get this range of possible results. And then it was up to them, and they said, well, maybe 25th percentile is a good target to go for, and use this as an orientation for the then following design competition. Also, after the design competition, this is now another project. Tool can be, or such tools, approaches can be used. And this was just to compare different design alternatives. And in this case, the one with the lowest impact was maybe not surprisingly one with a timber structure. However, it didn't win the competition, unfortunately, but at least the jury had this as additional information, this embodied carbon value to include in their decision making. And also a step later, when it's more toward the detailed design phase, you can use this information. For example, this is an environmental education center, which was built also in Germany. And the architects from the beginning had this idea to have this rammed earth wall running through the building as a part of their concept and holding then also this roof. And then when the contractor came into play and they did the cost calculation, they said, well, concrete is much cheaper, can we use conventional reinforced concrete? And then the architects used the tool to compare this conventional concrete wall with their rammed earth wall and could show that actually big reduction in impact using the rammed earth wall. They also tested some other alternatives, such as using different foundations or different flooring, where you could improve the building further, but the impact was not that big. So finally, they used the information to convince the client to go for the rammed earth wall and then go for the financially cheapest option. And there are many more kinds of applications. This was just a quick jump into it. And we said we could also let the computer do the work. And there I want to show one example of a single family house retrofit. So imagine this could be your little summer house somewhere, and you want to make it more energy efficient. So you have different options. You could add additional insulation on the wall, on the roof, on the basement ceiling. You could exchange the windows. You could exchange the heating system. So in theory, combining all of these materials, there are more than millions of solutions. If you want to know now what's causes the least global warming potential over, for example, lifetime of the next 20 years, looking at the operation and the material related impacts, you can use the computer to identify this optimum. So this genetic algorithm starts by coming up with random solutions, then recombines the best ones, eliminates the worst ones, and then slowly converges. And whenever a new optimum is found, such a little triangle here is plotted. Now, we cannot be sure that the global optimum is really found, but we can only trust that after a certain time, in this case 30 generations without a new optimum, we have found the best solution, or at least we're very close to the best solution. And then the algorithm proposes this as the final solution, and you as an owner can use it for your decision making. Now, if you're the owner, you're probably also interested in cost. So you could also combine this with additional criteria, and then you use a multi-criteria optimization, and for example, plot the results based on investment cost and the life cycle global warming potential. And then you see in the special case here in red, this Pareto front, those are all the solutions that are optimal because you cannot improve them towards one criterion without becoming worse towards the other one. And in this special case, we see a very flat part here, meaning for a little more money, you can save a lot of greenhouse gas emissions, while afterwards it's quite linear. So in this case, this could help then maybe to go for the little more expensive solution, but actually save a lot of global warming potential. Now, how do we develop this further in the future? Well, we have in the group working different PhD students on topics, and this is only a few of them. So one is actually to go and also the Swedish context and to see how can stakeholders apply these tools in real projects. What do they need to actually save carbon in the real world? Another big thing is, of course, AI. So we look at how can machine learning further simplify and speed up the calculations. And then also interestingly is how do we scale up from a single building to a neighborhood where we can use more synergies, but we also have maybe to refine functional units. And that's a big part. To summarize, I think the climate declarations, it's great as a start. They're in place. They'll only look at the production-related impacts. So to go one step further, we need optimization of the whole life cycle. And I think one promising approach to use these computational tools that can support designers and decision makers. I hope I could give you now a small glimpse into this, but there are many more options. So here I want to say thank you very much for your attention, and I look forward to the discussion.
Thank you, Alexander, for your presentation. Great. Now it's time for questions. And if you have a question, please use the Q&A function here in Zoom. And so you can take some time, write your questions, and I will pick them up soon. I will start with a question here, Alexander. Do you see a risk of oversimplifying LCA calculations with digital tools like you presented?
Yeah, that's a good question. And we also use those tools in teaching at Chalmers, and that's I think, very helpful to actually use LCA, for example, in an architectural design process with students. But after the last course, I asked the students, so what was surprising and what did you learn? And one student said, well, we still actually have to think. And I thought there was a big, a good learning that the tool can take out some efforts, reduce the effort, but at the end, especially the interpretation of the results is something that you still have to do. And in order to do this, you still need to have some knowledge about the whole idea of LCA and life cycle management. So maybe the tools can make it sound look easier than it still is.
Okay. Thank you so much. Let's continue with the second question. Are designers willing to use your optimization results, or do they want to control the design themselves?
Yeah, that's interesting. And I think that depends a lot. I think we have traditional designers who still think they're more an artist. They come up with the perfect proposal. At least that was my impression in Switzerland and Germany. Maybe in Sweden, it's a bit different where you work more collaboratively and you're more willing to accept also results that the computer generate. And I also think the younger generation of designers, they don't mind. They're so used to it. So they're happy to use the computer to propose solutions unless they can still control which one will be built at the end.
Okay. Thank you. Let's continue with this another question. How accurate are the models in early design phases based on a lot of assumptions?
Oh, yeah, that's, I mean, general, I think LCA challenge is working with assumption. And I think with working with buildings, we have the challenge that we have such a long use phase where lots of uncertain things happen. We have used in previous projects different tools or different approaches to model the uncertainty and then come up with robust results that perform well independent of the future change in the climate, for example, or uncertainties in the material or the replacement period. So I think there are ways to do it. But of course, we still, I mean, whatever the user does during the use phase, we're not sure. So we have to work with assumptions there.
I understand. Thank you. Yes, can you add additional calculations like daylight calculations, etc.?
Yes, that's something we are also working on now. And interestingly, it looks much easier on first sight than it is, because if we have this simple 3D model, typically some energy simulation constructed a bit different than for daylight simulation or for LCA. So it's possible to combine them. Interestingly, the complexity, I don't know if it grows exponentially, but at least it grows a lot when you combine them. But we have one PhD student working on exactly this, trying to combine different environmental performance criteria into one tool.
Okay, great. Thank you so much. Now I will pick up some questions from the Q&A. So if you have a question, please enter it in the Q&A function here in Zoom. The first question is from Emmanuel. Is it possible to do LCA on renovations with Kala? Renovation, rebuilding, transformations, and so on will likely increase in the future. What is possible today, and how do you work to stay relevant for these projects?
Yeah, that's a yeah, in the European context, I guess that's very relevant. We should rather retrofit the existing stock than build new. And yeah, I say of course, but yes, the tools can help there. And first of all, to show like in the little single family house, this could also be done on large multifamily buildings or office buildings, to say if we renovate, how much embodied carbon do we have to invest? When does it pay off? Does it make sense? Under which circumstances? And then I think another interesting field is densification of cities, or adding stories on top in city centers, where it becomes interesting to discuss, yeah, what's the functional unit. And but I think there it's really powerful to show or to use the tool also the worth of the existing building stock, instead of just demolishing and rebuilding, to show how much embodied carbon is there, how the value of the existing building.
Okay, great, thank you. Let's continue with another question here from the Q&A. It's from Nilofar Saker. Thank you for the inspiring topic and presentation. Have you tried it on more complex projects in the bigger scale?
Yeah, we have big projects, meaning up to 30,000 square meters of built area. But I think complex buildings such as hospitals, laboratories, there it becomes very individual, especially for the use phase. There, I would say, yeah, you need still experts. It's difficult to combine everything in one tool. But as such, the size of the project is, I think, not doesn't matter that much. I think maybe as showed in the Outlook, becomes more interesting if you look at the whole quarter in the city, like in Gothenburg, this new Masthugskajen, for example. If you have different buildings, they shade each other. They could also provide one energy for the other. So then I think it becomes really interesting, and there we have to increase developing the tools. Yeah.
Okay, thank you. Yes, let's continue with another question here from the Q&A. Can we reach net zero carbon building now, or is it still far away? A question from Joseph El Kayat.
Yeah, interesting. That's Yeah, I think it depends a lot of your calculation framework that you use. Many claim that it's reachable, and I think, yes, using bio-based material, fast-growing bio-based material, and looking at the carbon stored in the material, it's possible to reach net zero carbon emissions. How to exactly define net zero carbon emissions on, especially on international level, that's still like, yeah, not very clear. And actually, we just started a new Annex 89, which is exactly called Net Zero Life Cycle Carbon Buildings, looking for the next 5 years, funded by the energy or run by the International Energy Agency to say, yeah, what's net zero carbon in the building sector.
Okay, interesting. Yes, thank you. Yes, and another question from the Q&A. Where is all the data in the tool from?
Yeah, and that's, well, here I showed the German version of the tool, and there's a database called ÖkobauDat and some standards. We have a similar tool developed now for teaching purposes at Chalmers. There we use this Bowerkes climate database as the background, which is those generic values. But you could also use environmental product declarations, EPDs, as the background, or we have one PhD student who linked his model to, at the end, EcoInvent using the Brightway software. So I think, yeah, there are many different data sources depending on the purpose of the tool and the complexity. Yeah, we can adapt a bit to make it, yeah, more simple or more complex, which gives you more options as the user then to, yeah, choose background data.
Okay, thank you so much. Let's see here. Yes, another question here from Crystal Carlson. Thank you for an interesting presentation. Ground constructions of buildings often involve using cement and steel, which generate high climate impacts. Could you also include impact from ground constructions in your tool?
Yes, we do currently, we do it, I would say, quite simplified, saying either you have a base plate or you have these pile foundation, you calculate the mass of concrete and reinforcement in those pile foundation, and you add it to the final result, and that works. There's no now soil model included that would help you to define how much foundation material you need. So I think there we would link to a structural design software. So this could be extended, but yeah, definitely groundworks can and should be included.
Okay, thank you so much, Alexander Hollberg. That was the last question. Thank you, Alexander Hollberg, Associate Professor at Chalmers University of Technology. Thank you for your great presentation and for all your answers here. And if you are interested to learn more about the field of LCA for optimization in early design phases of buildings, you will find more information in this selected publication and in these two selected publications. And all these links are available at the calendar post for the event at lifecyclecenter.se. And please feel free to contact Alexander if you have more questions. And here you can see his email address. The Life Cycle talks are published by the Innovation Cluster for the Life Cycle Perspective and the Swedish Life Cycle Center. And next talk will be given on October the 11th on attributional and consequential LCA with Thomas Ekvall at Chalmers. And to ensure you don't miss next Life Cycle talk, follow us on LinkedIn and subscribe to our newsletter. Thank you, Alexander, again.
Thank you.
And thank you all participants for listening.